Okay, we're going to continue on here, chapter 14, part 1. So we got a little bit into chapter 14 last time. We were talking about acids and bases in this chapter to start with. And again, a couple definitions, right? An acid is really something that can produce H plus ions or H3O plus ions in solution. In acid-base chemistry, as we talked about, pretty much they are interchangeable, the hydrogen ion and the hydronium ion. You can sort of interchange them both in sort of equations and also in formulas. They, again, basically mean the acid part. And if something is an acid, it does have that ability basically to produce free-floating sort of H pluses in solution. And as we'll talk about, obviously, that will affect things like pH. On the other hand, our bases are typically things that can produce hydroxide in solution. And same idea there, something's a base, it will have the ability in that solution basically to produce free hydroxides basically floating around. A more sort of general definition of an acid and base is the Bronsted Lowry definition. And the Bronsted Lowry definition is an acid is a proton donor, while a base is a proton acceptor. And this sort of creates a relationship of partners in an equation. So, for example, if you had your HCl plus some water, for example, here, in this case, our HCl is our acid, and water actually is going to act as our base in this case. The acid is going to send the H plus over to the water. The result of that is here we will produce H3O plus and really our Cl minus. And in this case, the HCl on the left-hand side is related to the Cl minus here on the right-hand side, and that is what's known as its conjugate base. The H2O and the H3O plus are related to each other, and that is what is known as its conjugate acid. So it creates these conjugate acid-base pairs sort of on the other side of the arrow. Usually our regular acid and bases are found on the left-hand side, and our conjugate partners are sort of on the other side of the arrow. As we talked about, it's really important to know that, again, this is the only difference that there can be uh, if, if these guys are going to be partners. It can only be a 1H plus difference for them to be partners. As we go from the acid to the conjugate base, we have one less H plus as it donates it over. And as you go from the base to the conjugate acid, it has one more H plus as you go in that direction. This also is an example of what we were talking about a second ago between these two things. This is really just a strong acid dissociated in water. You could also, again, write this equation just like this, which commonly is written without the water. And in this case, you will get H plus versus H3O plus. So these two equations here do represent really the same thing. Again, it's just the strong acid dissociating basically in water. And like I said before, I personally will probably write it like the bottom way, but books and stuff do include the water a lot with the acids. And that's how you, again, produce the H3O plus. Remember that you can kind of think about these backwards when you're asked to write a conjugate acid or base. So if you're asked to write either a conjugate acid or a conjugate base, so if you're asked to write the conjugate acid, you can think about it in the backwards direction. And then what you're looking at in that case would be a base. You could just go by the definition of a base, which means you should put the H plus on. If you're asked to write the conjugate base for something, then if you go backwards, what you're looking at is actually an acid, which means you should get rid of the H plus. It is important, again, as we talked about last time, that that plus part does make a difference. It changes the charges on things. So again, if somebody gains an H plus, they do become one more positive from where they started. If somebody loses an H plus, they become one more negative in terms of their charge from where they started. And that's something people very commonly miss when they write these things, is sort of the charge aspect and how it changes. Any questions on any of that stuff there? Lastly, as well, I think we all talked about things that can act as an acid or a base, and those things, again, are amphoteric substances, and water is an example of that. And speaking of that, water can act as an acid or a base, which means it could actually react with itself, which is always happening sort of in a water solution. One would act as an acid, and the other one would act as a base in this case. And here, you know, depending on which one we label there, acid, base, we would get our partners here again in this sort of relationship. And this relationship is actually an equilibrium relationship. And because it's an equilibrium relationship with water, you can write an equilibrium constant for it, just like any other sort of equilibrium. It would be our products over our reactants, and in this case, that would be the concentration of H plus times the concentration of OH minus, adding to our list of Ks or Kc or Kp. This, of course, has to do with water, so creatively that is known as Kw, which is the ionization constant for water. This actually at 25 degrees, as we will see, does equal an actual value of 1 times 10 to the minus 14. So this relationship is actually a really important relationship. It allows us, in a sense, to calculate both the acid part of the solution, which is essentially represented by H plus. We could also calculate the base part of the solution, represented by hydroxide in this case. And we could actually use that to figure out whether or not a solution is acidic, basic, or neutral. So if we use this relationship of Kw, and by the way, that number of 1 times 10 to the minus 14 is an equilibrium constant value. It is probably the value you will use 99.99% of the time, but you should remember it is an equilibrium constant. As we talked about, the one thing that can actually change the value of an equilibrium constant is temperature. So if you happen to come across a problem, which you sometimes do, where they go, hey, we're doing this not at 25 degrees, you might be using a different value for Kw in those situations. Most of the time, they probably would give you the value, I would think, or have it in a table or something like that. But it can change with temperature like any other equilibrium constant. But for the most part, this is a fairly 99.99% of the time constant value that you will probably use along the way here. So how can we use this? Well, we could rearrange this and basically solve for the other concentration, regardless of which one you got, 1 times 10 to the minus 14 divided by the hydroxide concentration. Or if you have the hydroxide concentration, you could take 1 times 10 to the minus 14 divided by the H plus concentration. Definitely, for sure, in this chapter, if you are not doing it, you should still make sure you are doing it, which is make sure you use your exponent button, because you will definitely get the wrong answer if you're not using that exponent button as you punch these numbers in. So we could compare the H plus concentration to the OH minus concentration. And if the H plus concentration actually equals the OH minus concentration, by the way, at that point, they both will equal 1 times 10 to the minus 7 molar. You will have a neutral solution. If you look at the H plus concentration and it's larger than the OH minus concentration, which means the acid part is larger than the base part, then the solution will be acidic. And if you look at it, the OH minus is larger than the H plus concentration. That means the base part is larger than the acid part. You will have a basic solution. So this is a formula that if you know the H plus or OH minus concentration, you could calculate the other and figure out whether or not a solution is acidic, basic, or neutral. This is also, as I mentioned before, one of those equations where if you don't want to use H plus, you could swap in there H3O plus, and it's the same basic equation as well. Any questions on that there? So why don't you give it a try here. What is the concentration of hydroxide if you have an hydrogen ion concentration of 1.3 and Okay, so here we would use KW, and again, it is a value that you always have available to you, very rarely mentioned in a problem or anything like that. So it is H plus concentration times OH minus concentration equals 1 times 10 to the minus 14. In this case, we have the H plus concentration, which means we will rearrange this and divide to the other side. It is really the same calculation regardless of which one you're solving for. So we'll go 1 times 10 to the minus 14 divided by 1.3 in this case. And we'll go 7.7 times 10 to the minus 15. And we do need a unit as it is a concentration. So it should be molarity here. First off, any questions on the calculation? Again, make sure you're using your exponent button. That would make this one acidic, basic, or neutral. This one should be acidic. Again, obviously our H plus concentration is much larger at 1.3 than our smaller hydroxide concentration. And it's also an HCl solution, so that would be good too. All right, let's try this one here. We have H plus concentration 1.2 times 10 to the minus 6. What is the hydroxide acidic base? Okay, so once again here, going to look for the hydroxide concentration, which should equal our 1 times 10 to the minus 14 divided by our H plus concentration here. And put it in there, 1 times 10 to the minus 14 divided by 1.2 times 10 to the minus 6 gets you 8.3 times 10 to the minus 9 molar. Or if you have a calculator non-scientific notation, you got 1, 2, 3, 4, 5, 6, 7, and 8 zeros there with an 8 at the end, I think, because you ran out of space. So if you put it into scientific notation, you might get that one. Any questions on that there? Then we want to compare. So that's our hydroxide concentration. That is our H plus concentration. This is acidic, basic, or neutral. This one is acidic, it looks like there, perhaps number 4. A reminder again, if you are comparing exponents that are negative, the smaller negative exponent is actually the larger value. So in this case, the H plus would be the larger than the OH minus. And again, basically that means you're going 6 places that way and putting zeros, but that is 9 places that way with zeros, which makes it a much smaller number. So again, sometimes when people compare the negative exponents, they go with just the bigger number, but it's actually the smaller number is the larger one. Any questions on that one there? All right, so now let's talk about pH and the pH scale there. And the pH scale runs from 0 to 7 to 14. And below 7 is acidic. Above 7 is basic. And right at 7 actually is neutral. And as you go from 7 towards 0, you're becoming more acidic. And as you go from 7 towards 14, you're becoming more basic in that direction. And we could calculate the pH by using this equation, which is the pH is equal to minus the log of the H plus concentration. Once again, this is another one that if you wanted to switch out into H3O plus, it's again exactly the same thing. But here's the H plus. The name of it actually tells you what you need. pH means you do need the H plus concentration to calculate it. And when we talk about this formula, let's just talk a little bit about calculators, depending on the type of calculator you have as to how you would punch this in. So if you have a display calculator, you would punch it in exactly the way that you look at the equation. You would hit your negative button, you would hit your log button, and then you would put your number in using your exponent button in most cases. If you have a non-display calculator, you actually need to go backwards in this formula, and every other formula we'll kind of see in this chapter. You got to actually start with the number. You then got to hit the log button, and then you got to hit the negative button. How do you know if you have a display or non-display calculator? All you have to do is hit the log button. And if it says log on your screen, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. So that is the way you could tell. So again, display calculators, pretty much you could just punch in exactly where the formula is. If you have a non-display, you kind of have to usually work backwards on these sort of formulas as we go through it. So if the H plus concentration equals the OH minus concentration, then you will have a H plus concentration of 1 times 10 to the minus 7, and that will give you a pH of 7 on the nose for neutral. And that is what we're going to go with in this class. That 7 on the nose is neutral. Anything above it or below it is slightly acidic or slightly basic, depending on which way you go. Unless it's like, second decimal rounding into 7, then you could call it neutral. But if it's really not that close to it, we're going to go slightly acidic or basic. If the H plus concentration is larger than the OH minus concentration, and by the way, the relationship between H plus and OH minus is they run opposite of each other. So as the H plus concentration goes up, the OH minus concentration goes down, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. So if you have a greater H plus concentration, you're going to have a lower OH minus concentration, and you will have an acidic pH, which is a pH of less than 7. If you have the OH minus concentration, which is larger, that would mean that your H plus concentration is lower, and you will actually have a higher pH above 7 is what you should look at. The pH goes up as the H plus concentration goes down. And again, that is because at that point, the OH minus is going up. And vice versa, the pH will go down as the H plus concentration goes up and the OH minus concentration goes down. So again, those are the relationships there. When you are asked, is a solution acidic, basic, or neutral? By the way, there is just one answer for that. Yeah, so it's either acidic, basic, or neutral. It is not acidic and basic at the same time. I've never really had anybody go for the trifecta of all three together, acidic, basic, or neutral. But it does happen. Sometimes people will classify the same solution as acidic and basic because they're looking at the wrong thing. So it should only be one answer for that question, and always look at the pH scale, because for most people, that is the scale that you have basically in your head. So let's talk a little bit about pH and sig figs. And the number of decimal places in the pH type value equals the number of significant figures in the concentration value. So for example, here, if we had an H plus concentration of 1 times 10 to the minus 5, calculate the pH here with the proper digits. Obviously here we would use our pH is equal to negative log of the H plus concentration, putting our number in and obviously punching it in correctly depending on which calculator you got. On your screen there, you should probably have a 5 staring at you at that point. And that gives us some options. Should we record 5, 5.0, bless you, 5.00, 5.00000. That feels like a lot of zeros. So we'll get rid of that one. Which way should we record the answer here? This one? It is actually this one. So this number has 2 significant figures, which means it should end up with not 2 sig figs, but 2 decimal places. Yeah. So again, we go from significant figures in the concentration to how many decimal places you should have in your pH type value. By the way, it works the same way if you're going backwards, which we'll talk about. If you're going from the pH and you calculate something like the H plus concentration, however many decimal places your pH value have is how many significant figures your concentration should have. So it should work both ways in this case. Any questions on that? By the way, that's acidic, basic, or neutral. That is acidic. It is less than 7 in this case. By the way, if you have anyone that is 1 times 10 to the whatever, the pH will always be the exponent as long as it's a 1, right, in front there, because it will always be that way. So there's our pH scale, and again, we could see some things there like sodium hydroxide, which is a strong base up there at a pH of 14. We have some HCl there, which is a strong acid. We have pure water, which is 7. By the way, if you have water out and you check the pH, will it be 7? It will not. It'll probably be like in this range there, and that's because as it sits out, it will pick up some carbon dioxide and a little water and some CO2 makes a little carbonic acid, increases the H plus concentration a little bit in that solution and causes the pH actually to be a little bit more acidic in that case. We got vinegar, lemon juice, stomach acid, all acidic along the way. Now, that is a pH meter, which is obviously one way that you can check the pH of a solution. It's actually a probe that has an electrode in it, and it measures the H plus concentration floating around in that solution. You do it by calibrating it really with voltages, and it does like a calibration curve, and it figures out the voltage of your solution and goes, okay, then that's a pH of whatever it may be. That is a classic Beckman one. Now, there are similar sort of scales to pH. There's the pOH scale, which, as you might imagine from the name there, measures the OH minus concentration. So pOH means you need the OH minus concentration, and that is negative log of the OH minus plus. And the nice relationship is if you have the pH plus the pOH, it equals 14. So we add our pH in there that we just had there, minus the log of the H plus. There's a really nice relationship between those two. That means it does give you some options. If you have the OH minus concentration and you want the pH, you could actually calculate the pOH and just subtract 14, and you'll have the pH. You could also still use KW like we did earlier. You could use the KW to go from the OH minus to the H plus and then go into the pH equation. So there's a couple of different sort of avenues that you could get there. Now, adding to our sort of list here, if you have the pH, you can get directly from that the H plus concentration. And to get the H plus concentration from the pH, that is the inverse log of the negative pH. I would say on most people's calculators, when you do the inverse log, that is the 10 and a caret. It usually pops up there, also known as how a lot of people do scientific notation incorrectly. This is actually what you should use it for. And if you have the pOH, you could get directly from that the OH minus concentration. And it's really the same calculation. The OH minus concentration will equal the inverse log of the negative pOH. And once again, that's usually a 10 and a caret negative pOH in this case. Again, on most people's calculators, usually to get to the inverse log, your top left corner, your second button are like a shift button. And then on the log, usually above it's like 10 to the x, and that is, again, the inverse log, basically how you get there. Same thing with that one. If you have a display calculator, you would go shift log and then negative pH. If you have a non-display calculator, you would have to start with the number. You would have to make it negative and then do shift log. So again, you kind of have to work backwards if you have a non-display calculator, if you're going to do that. So with all these options here, there are, again, multiple ways that we could kind of get to the answer we're looking for. Now, I said earlier that there is only really one answer to the question of is it acidic, basic, or neutral? And just so we're clear, if you look at the pH scale, that's our 0, 7, and 14. Once again, acidic this way, basic this way, and neutral this way. Just so you understand, the pOH scale also goes from 0 to 7 to 14, except it runs opposite. So this is acidic, this is basic, and this is still neutral. And if you have a high pH, you actually have a low pOH and vice versa. They run opposites of each other. This is how people get to the answer of, I think the solution is acidic because the pH is less than 7. And then they go, well, I think it's basic because the pOH is above 14. And then they get like some X's. Yeah, so you don't want to do that. Again, I would say probably most people, this is the scale that they have in their head. And this is the number you should look out to determine if it's acidic, basic, or neutral. Again, this runs opposite. So that's how, again, I think a lot of people give that answer of multiple things for the same solution. So always look at the pH because, again, that's always the scale that you are running for. Yes. Any questions on that there? Okay. Of course, I wrote that backwards, so let me fix that, so that will make sense there. So hang on a sec. There we go. So this is basic. There we go. And that is acidic. That would make a lot more sense with that conversation we just had. There you go. So yeah. So again, if it's acidic on the pH scale, it's going to be higher than 7 on the pOH scale and it'll be acidic. And again, basic on the pH scale will be less than 7 that way. Sorry about that. So swap those guys around there. All right. So I'll give it a try here. We got a pH of rainwater at 4.82. Let's just make sure we know how to do everything. So let's calculate the H plus, the OH minus. Let's do the pOH, and is it acidic, basic, or neutral? And for the bottom one, we have the hydroxide given to us. So let's calculate the pH, the pOH, the H plus concentration, and is it acidic, basic, or neutral? Okay, let's take a look and see how you're doing. So, like I said, with those formulas we just saw, you do have a few options as to what you want to attack first here, since we're looking for everything. So since we do have the pH here, I could get the pOH if I wanted to, because the pH plus the pOH will equal 14. So the pOH here would be 14 minus our pH of 4.82, and that would get me there 4.82, 9.18 as our pOH here. I do have the pH and the pOH, which means I could use each of those to get the concentrations of H plus and OH minus. So from the pH, again, I could get the H plus by taking the inverse log of the negative pH. So again, on your calculator, probably show a 10 a caret, negative 4.82 is what you want to punch in there. And if I can find my button, there it is, 4.82. That is going to get us here a 1.5 times 10 to the minus 5. We do need a unit because it is molarity. At this point, you actually still have two options. You could also go back to kW and just use kW like we did before. So option 1 would be, at this point, you could get the OH minus by taking 1 times 10 to the minus 14 divided by 1.5 times 10 to the minus 5. And that's our kW formula. Or you could do the same thing as we did for the pH here and do the inverse log of our pOH, since we have that. So why not? We'll do that one there. That's going to be a 10 a caret, and our pOH was 9.18. And that's going to get us here. We'll go 6.6 times 10 to the minus 10 molar. And again, if you kind of took the KW route, you really should end up with the same number, maybe slightly off with the rounding, but pretty much the same number if you did KW as well. Maybe you get 6.7 with the rounding if you did some rounding along the way there. At this point, we also want to know, is it acidic, basic, or neutral? In this case, again, we want to look at the pH only, and that is less than 7, which means it should be acidic in this case. Any questions on any of that there? Now, in terms of sig fig wise, we had 2 decimal places gives us 2 significant figures when we go again backwards, going in that direction there. All right, taking a look at the bottom one here, we have the hydroxide concentration. Again, you have several things you could start with. If you want, you could go right into the POH because you do have the hydroxide concentration and calculate that. And that would get you a POH minus the log of 2.5 times 10 to the minus 7. And that is going to get you looks like 6.60. At this point, you could also get the pH very easily by just taking 14 minus the POH, which would get us 14 minus 6.60. And that's going to get us there 740. It looks like 7.40. Again, at this point, you have options. Now that you actually have the pH, you could use the inverse log like we did on the first one, or you could have originally as well used your KW and went in there and got it. Again, both should give you the same answer. So just to mix it up a little bit, we'll do KW on this one. The H plus concentration will equal 1 times 10 to the minus 14 divided by our OH minus 2.5 times 10 to the minus 7. And that's going to get us here. Looks like maybe 4.0 times 10 to the minus 8 molar. Again, we need units as that is a concentration. And again, we basically had 2 decimal places, 2 significant figures going that way as well. Also, if we did just KW, 2 significant figures basically from that guy as well to get us there. That leaves us lastly here. Is it acidic, basic, or neutral? This is going to be slightly basic in this case, just above 7. Yeah. Any questions on any of those calculations there? Obviously, again, you could have started with KW, got the H plus, then you could have went into the pH equation, got the pH. So again, it does give you a variety of ways that you could get there, but depending on whichever way you choose, they all should really get you to the same answer at the end, as long as you do it correctly. Any questions on any of those there? All right, one more here, maybe. Environmental chemists obtained a sample where the H plus concentration of rainwater was 3.5 times 10 to the minus 6. We're looking for everything in this case, and let's add our normal. Is it acidic, basic, or neutral in this case? Yeah. Okay, so let's take a look again here. We are given the H plus, so 2 options. You can get the OH minus concentration using KW. You could also just get the pH. So I'm gonna go with the pH first here. So our pH is gonna be minus the log of our H plus, which is 3.5 times 10 to the minus 6. And that's gonna give us a pH here of 5.46, looks like. Once I have the pH, I could actually get the POH the same way by subtracting 14 that we did with the pH last time there. So if we subtract 14 from that there, that's going to give us our POH. Looks like 8.54 at this point. Again, we have both the pH and the POH, so we could use the H plus concentration is the inverse log of the minus 5.46. Again, that's probably going to look like a 10 and a caret on your calculator there. Again, you could also use your KW, right, to get it as well, since you have the we already actually have the H plus, so we don't need that. So we could do that. Maybe the OH minus would be good, since that's what we're looking for there. OH minus would be the inverse log of our POH, which is 8.54. And we will get the same answer there previously there. All right, so let's try that one there. And we'll do our minus 8.54. That's going to give us a 2.9 times 10 to the minus 9 molar. Once again, you could use still kW to get your OH minus concentration as well. All right, so let's see. I got that, I got that, I got that. So we're just at acidic, basic, or neutral. We're going to look at our pH, which is definitely less than 7. So we are acidic in this case, yeah. Any questions on that one there? All right, so obviously you need to be able to calculate pH, POH, H plus, OH minus, determine if it's acidic, basic, or neutral. Again, as we've seen, there's multiple ways you can kind of get there. Any questions? All right, then let's talk a little about acids and bases and electrolytes. A reminder that, as you may know, electrolytes are really solutions that when they go into, or substances that when they go into solution, will break apart into ions. And electrolytes can't conduct electricity because of the presence of those ions. We have strong electrolytes, which 100% break apart. It's basically a one-way street. So if you have something like sodium chloride in solution there, you pretty much are only going to have the ions. You will have none of the sodium chloride units left. You would have 100% of that. If you took something like hydrochloric acid and dumped it into a beaker, it also would 100% break apart into H plus and Cl minus. You would have none of the HCl units basically still together. On the other hand, a weak electrolyte is something where we have our forward and reverse reaction, these arrows that head in both directions. And unlike a strong electrolyte, a weak electrolyte will pretty much stay together. But it will break apart a little into these guys. So for example, if you had acetic acid and you dump that in there, in the solution, you actually would mainly have acetic acid molecules floating around, but a little bit of it will break apart into acetate and H plus. So since it's still able to produce a little bit of H plus in that solution, it is still considered an acid, but it's considered a weak acid because it's not going to produce anywhere near, for example, the amount of H plus that HCl will, because when HCl goes for a swim, it's going to completely break apart. Nobody's staying together. But really, when acetic acid goes for a swim, it's going to pretty much stay together, and a little bit of it's going to break apart. So that's a strong electrolyte and a weak electrolyte. And strong acids are strong electrolytes, and there's really a list of 6 strong acids that you really should know. And that's pretty much most of the list down there on the bottom. But strong acids, we have hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. These are kind of the 6 really strong acids. The reason it's really good to know that is if it's not one of these 6, it's probably a pretty good guess that it's a weak acid. So kind of like by process of elimination, if it's not one of these 6, then you could probably, like I said, make a pretty educated guess that it's going to be more of a weak acid than a strong acid in that particular case. Here, this is really just a dissociation of these acids and water. And since we do have water in each of these cases, the H plus will go over. And in this case, we will make H3O plus because the water is included, and Cl minus, H3O plus, and NO3 minus, H3O plus, and ClO4 minus, and H3O plus, and HSO4 minus in this case. And again, it's pretty much going to be a one-way street for most of these guys, and they're going to produce a lot of H plus really quickly in solution. And once again, each of these equations are the same as we talked about earlier, that you could write each of these without the water. And again, it would look something like this, which is basically an equivalent equation to each of those. Just take the water out and you get H plus instead of H3O plus on the other side. Now, weak acids, on the other hand, like I said before, are weak electrolytes, so they will mainly stay together. So here we're going to still get our H plus transferred over. We'll get H3O plus and F minus. We'll get H3O plus and NO2 minus. We'll get H3O plus and SO4 2 minus, and H3O plus and OH minus in this case. So again, each of these would stay together pretty much, but you would have a little bit. So once again, if you had your HF, you mainly would have HF guys together, but a little bit of it will break apart. Same thing with our weak acids as our strong acids. You could write this reaction without the water, and it basically will look like this. Yeah. Looks the same without the H3O plus, you just get the H plus. And again, that's perfectly fine as well. Now, strong bases are strong electrolytes, so much like our strong acids, they will 100% break apart in solution, which again is why they are strong bases, because they will generate a lot of hydroxide in that solution really, really quickly. So if you had some sodium hydroxide you dumped in there, you're going to get a lot of sodium ions, but more importantly, in terms of the pH there, you're going to get a lot of free OH minuses really, really quickly. And again, as the OH minus concentration jumps, the H plus concentration lowers and the pH goes up a lot, right? Because you got a lot more base than you do acid in that case. In terms of our strong bases, as I mentioned before, pretty much group 1 and 2 on the periodic table is where you're going to find those. So start like lithium to sodium to potassium, hang it right there at calcium, a little strontium and barium. Pretty much this 6-pack here with hydroxide is going to make a lot of your strong bases that you can find, again, from group 1 and 2 on the periodic table, which are our alkali metals and our alkaline earth metals. And again, the word alkaline means basic, so that's where a lot of our strong bases really come from. So again, as you can see here, sodium hydroxide, potassium, barium hydroxide, considered strong bases. Our weak bases, on the other hand, usually do not have hydroxide in them, but they will accept actually the H plus from the water, and they will actually produce the acid they come from in each case and produce hydroxide, which again is why they are bases in this case. Now, as I mentioned before, usually for acids, people a lot of times will not include the water in sort of dissociation reaction, but it is a really good idea for the bases to include the water when you're writing the reaction or the equation, because sometimes when people don't include the water for the bases, they have a hard time visualizing where the hydroxide comes from. So sometimes it's a good idea to include the water in the reaction when you're writing it for a base. If you want to include it for the water, there's nothing wrong with it, but sometimes you can leave it out of the water for the acid and stuff like that. So what is the relationship here between our conjugate acids and conjugate base pairs? Well, there is an important relationship that we'll talk about in this chapter as well, which is if you have an acid, it will have a conjugate base. And if that acid is a strong acid, its conjugate base will be considered very weak. And what that essentially means in this case is it will essentially just kind of hang out and do nothing. It won't continue to react. So it's going to be really weak. It will still be there, but it's not going to really cause any problems in terms of the pH. It's essentially, as we'll talk about, neutral. So it's just kind of a neutral little sky hanging out, floating around, not really doing too much. If you have an acid that is a weak acid, its conjugate base will be relatively strong. Now, what we mean by relatively strong is it has the ability to actually continue to react with water. And those sort of conjugate bases can actually continue to react with water in a reaction known as a hydrolysis reaction, and it can actually affect the pH. Now, these conjugate bases are not strong bases, but they're strong in the sense that they can continue to react. For example, right there, that would be one right there. That is a conjugate base that's relatively strong in the sense that it will go through a hydrolysis reaction, which is it reacting with water. And as you can see, what it will do is it will actually form some hydroxide, which means you would actually consider this solution to be more basic because it's going to, that salt being there is going to continue to produce hydroxide, and that's going to affect the pH of that solution. Same thing works with a base. They have, again, sort of the opposite relationship. The base and its conjugate acid. If you have a strong base, its conjugate acid will be relatively weak or essentially neutral. And if you have a weak base, its partner will be relatively strong. Again, not as strong as a strong acid, but strong in the sense that it can continue to react with water and affect the pH of that solution. So H3O plus is the strongest acid you could have, and OH minus is the strongest base you could have. Any questions on that there? So sort of an opposite relationship, and it's really important as we go through this chapter and do some calculations that you understand that a lot of times where something comes from gives you an idea of what is it going to do? Is it going to react or not react? Here's a table from your book of some relationships there. Again, we have our kind of strong acids up here. Partners on this side relatively weak. Our more weaker acids, partners on this side relatively strong, or however you want to look at it in that case. So again, strong acid completely dissociates into ions, and a weak acid will basically stay together. So why is that important? Well, for example, if we had a strong acid actually given to you, say like hydrochloric acid, and we get H plus and Cl minus in this case. Now, if we know the concentration of this guy is, say, 0.1 molar, in terms of the pH, it's actually the H plus concentration that's really important, as if we wanted to calculate the pH of this solution, it would be minus the log of the H plus concentration. We could figure out the concentration of our H plus by just doing a little stoichiometry. It's a 1-to-1 relationship, which means the molarity here of the H plus would be 0.1. By the way, the molarity of the chloride would also be 0.1, as it's a 1-to-1, but not that important in terms of the pH in this case. That would allow us to go actually into our pH equation and actually get, again, our pH of about a pH of 1 there as we do that there. Which is acidic. Now, if we had a strong base, same idea. If we had sodium hydroxide, it would completely break apart into a sodium ion and a hydroxide ion. The difference here is it is a base, which means we actually would have the hydroxide concentration. Again, if this was 0.1 molar, it's a 1-to-1 relationship, 0.1 molar. This would not give us our pH directly, but it would get us our pOH. And again, here we would put that in, minus a log of 0.1, going to give us 1 for our pOH, which, if you know that is a base, would not make sense if you thought it was the pH, but you could get the pH by taking 14 minus 1, That's going to be a pH of 13, which is basic and would make sense for our strong base. So a lot of the times you're given kind of like generic H plus or OH minus concentrations, but occasionally you may be given an actual formula. And if that formula is a strong acid or a strong base, you could use it to figure out either the H plus concentration or the OH minus concentration. Then you could go into either the pH or the pOH equation to do that. Any questions on there? All right, so why don't you try a couple here? What is the pH in each of these cases? Got nitric acid and barium hydroxide. Okay, let's take a look. So first off here, we have nitric acid, which is a strong acid, which means it's a strong electrolyte. It is one of those 6 there that you really should know. That's going to break apart into H plus and nitrate. And obviously here, in terms of the pH, that is the most important thing. Since we do know the concentration of the whole thing here, 2 times 10 to the minus 3, it is again a 1-to-1 relationship like it usually is with most strong acids since they're monoprotic. The concentration of our H plus would be really the same concentration here. And that would mean that's all we need to go into our pH minus the log of the H plus concentration. And that gets you minus the log of 2 times 10 to the minus 3 molar. And that's going to get us here, looks like a 2.70 here, which is an acidic pH. A reminder, if you're not sure why that is in terms of the concentration, when we look at 2 times 10 to the minus 3 moles per liter of nitric acid, we're really just doing like a little stoichiometry here. For every 1 mole of HNO3, there is 1 mole of H plus. The moles cancel, gets you your 2 times 10 to the minus 3 moles per liter of H plus. And clearly this has one significant figure, which really this should be a 2.7 in terms of the actual correctness of sig figs there. Any questions on that there? All right, taking a look at the bottom one there, that is barium hydroxide, which is one of those strong bases, which means it's going to break apart here. And it's going to break apart into a barium ion. And you actually will get 2 hydroxide ions here. That means in this case, it is the OH minus, which is of interest. And we have 1.8 times 10 to the minus 2. It is actually a 1-to-2 relationship, which means you do have to multiply the concentration by 2 to get the correct concentration of the hydroxide, which is 0.036 molar in this case. And again, that is the correct hydroxide concentration. Again, basically, we just did the same thing we talked about above there. 1.8 times 10 to minus 2 moles per liter of barium hydroxide, doing a little stoichiometry, mole to mole relationship. For every 1 mole of barium hydroxide, you get 2 moles of OH minus, and that's going to cross those guys out, giving you our 0.036 moles per liter of hydroxide in this case. So if something doesn't break apart into a 1-to-1 relationship, you basically can quickly just multiply by the coefficient, the molarity, and it will give you the right one. So if you have something broke apart into 1 to 3, you would multiply the molarity by 3. That's going to give us our hydroxide, which means our pOH, not our pH, is going to be 0.036. That is going to get us here 0.036. A pOH of 1.44. The pH then will then be 14 minus that 1.44. And that's going to give us a basic pH, which we would hope would be here for our base of 12.56 in this case. Any questions on either of those there? So again, it's important to make sure you do get the correct sort of concentration. I would say probably out of the two, probably your strong bases, you might come across that a little bit more than you will with your strong acids, as those 6 strong acids, for the most part, 5 of the 6 are, and most of them are monoprotic, so you'll just have 1-to-1 relationship. But sometimes with the base, you do have